Here are the problems on oscillations. Number one, got to find the spring stiffness constant using force divided by extension. Force is 2.7 times 9.8, which is mg, divided by the extension in meter. And of course the amplitude is 2.5 centimeters. You do not have to add the 3.6 centimeter because that will be the new equilibrium position. And then to find the frequency, use the formula 1 by 2 pi square root k by m. You get 2.62 hertz. In question 2, the frequency is 3 hertz and the amplitude is 0.13 meter. Mass is given as 0.6 kilogram. Omega is 2 pi f. Omega is called the angular frequency. It is 18.84 radians per second. Velocity at the equilibrium position is the maximum velocity. That happens when x is 0 because you measure displacement from the equilibrium. You get it as 2.45 meter per second. This is the C part. The total energy is 1/2 m omega squared a squared or k a squared. You get, when you put in the numbers, you get 1.8 joules. And now the B part is to find the velocity when it's 0.1 meter from equilibrium. So x is 0.1 meter. Use the formula as before. Get the answer is 1.56 meter per second. And the equation is A cos omega t. Therefore it's 0.13 cos 18.84 t. In number 3, the equation is given and you compare it with the general one, which is x is a cos 2 pi ft. And immediately you see that a is 0.45, 2 pi f is 6.40. So from that you can find the frequency as 6.40 divided by 2 pi, which you get as 1 hertz. And then you have to find the total energy using 1/2 m omega squared a squared. Which gives 2.48 joules. And then you have to find the kinetic energy, which is 1/2 m omega squared a squared minus x squared. And x is given as 0.3 meter. And that's 1.4 joules. Now potential energy is 1/2 m omega squared x squared. You can also find it as total energy take away the kinetic energy. Both will give the same answer, which is 1.1 joules. In number 4, frequency is 1 by 2 pi square root k by mass. K is 20, mass is 1.5, so you get the frequency. You got to find the maximum speed, which is a omega in the B part. And remember that omega is square root k by m. So first find omega and then plug it back into relation. You have 0.365 meter per second. Where does this occur? Of course, at the equilibrium position. That's where the speed is maximum. And now the maximum acceleration is omega squared a. That's the maximum acceleration. It happens when the object is at the amplitude position. So m negative just shows the sign anyways, so you get 1.3 meter per second squared as the maximum acceleration. And where does this happen? Of course, at the amplitude. And again, as before, total energy is 1/2 m omega squared a squared or 1/2 k a squared. That's 0.1 joule. Expressing the displacement as a function of time, x is a cos omega t. So now we know that's a, it's cos omega t. In number 5, the bullet is fired into a block which is attached to a spring. The amplitude is given, so it's 0.215 meter. We know that the total energy is 1/2 k a squared, so the spring constant is given, so that's k, and plug those numbers and you get 177.9 joules. And now the most important thing is to know that this total energy is equal to the kinetic energy. So that's why it's 1/2 the sum of the masses times the velocity squared. And rearrange to find the velocity squared as ka squared by the sum of the masses. And you get the velocity as 23.86 meter per second. Now that's the velocity with which they both started moving together. Now from which we have to find the speed of the bullet. Okay, so we use the conservation of momentum. Vb is the velocity of the bullet, and so which is what we're looking for. And when you plug the numbers and calculate, you get 596.5 meter per second as the velocity of the bullet. Approximately 597. Question number 6 is about a simple pendulum. Length given, the mass is given, and the angle that it makes with the vertical is also given. Frequency of oscillation is just 1/2 pi square root g by the length. Plugging all the numbers gives 0.57 hertz. That's a diagram of how it is oscillating. From this diagram, you can see that x is the displacement, which we can calculate using the angle. But the angle has to be converted into radians first. So first we got to convert the 12 degrees into radians. And then use the formula x is theta times the length, because the length of the arc, x, is the angle in radians multiplied by the length. Now 12 times pi by 180 changes degrees into radians. 12 times pi by 180. That's why you see that there. This is in radians now. And then multiply with the length and you get the length of the arc as 0.159 meter. And you're looking for the pendulum's speed at the lowest point, which is going to be maximum. Therefore, it's a omega. That will be 0.159. That's the amplitude. So that's an important point, because x here is the amplitude, which is 0.159, which we have used here, times 2 pi f, and you get the answer. In the C part, you have to find the total energy. Once again, it's 1/2 m omega squared a squared. and get it as 0.0592 joules. In number 7, spring constant is 60 Newton per meter. The force is 5 Newton. So you can use F is equal to negative kx and find x. That's 5 by 60, which is 0.083 meter. And that's the amplitude, and that's what we're looking for, 0.083 meter. And in number 8, you're asked to find the total energy. Mass is given, K is given, and maximum velocity is given. But we know the maximum velocity is A omega, right? Okay, and can use that. And also, E total is 1/2 m omega squared A squared. Now from maximum velocity, A omega, if you take a look here, you see that this is A squared omega squared, and so all you got to do, remembering that Vmax is A omega, is just square the 1.5. And you get it as 0.56 joules. In number 9, you have to find the maximum kinetic energy. And you know the maximum kinetic energy is the same as the total energy. Therefore, in fact, that's also equal to the maximum potential energy. So you use 1/2 m omega squared A squared. Or 1/2 k A squared, which is what you use here. Again, it's 0.625 joules. You have the amplitude, and you have K, which is actually m omega squared. Number 10, got to find the frequency. It's straightforward. 1 by 2 pi square root K by mass. Substitute the numbers. K is 18, and the mass is 2. So you get 0.48 hertz. 11, it's about a pendulum. The mass does not affect the period, so that's immaterial. The length is given, and we know that G is 9.8. So using that formula, T is 2 pi square root length by acceleration to gravity gives you 10.78 seconds. Once again, mass does not affect the period of a simple pendulum. In 12, it's exactly what I was telling you before. Frequency of a simple pendulum is not affected by the mass. And hence, if you change the mass, the period is, or the frequency, is going to be the same as before. So it's 2 hertz. As long as you don't change the length or don't change G, the period or frequency will be the same for a pendulum. In 13, you've got to find where the kinetic and the potential energies are equal. So set them equal. Ke is equal to Pe, and you know the formula for Ke is 1/2 Ka squared minus x squared, which is equal to 1/2 Kx squared for potential. Simplify that and take that negative x squared to the other side, so it becomes positive. 2x squared is a squared. X squared is a squared by 2. X is square root of that, which is a by root 2. And what's given here is the maximum velocity, but we know maximum velocity is a omega. So set that a omega is equal to, is it 1.5? Yeah. So a omega, or can be also written as a root k by m. So hence you find a, which is the amplitude, and which you get as 0.24, and then plug it back into that equation to calculate x as 0.17 meter. In 14, it says, where is the period greatest? And that's about a mass oscillating at the end of a spring. And the period of an oscillating spring does not depend on the acceleration due to gravity. So it'll be the same on the Earth and the Moon. That's for a spring. 15. If you increase the amplitude of a mass and spring system, what happens to the resonant frequency? The resonant frequency does not depend on the amplitude. So there is no change in the frequency. Resonant frequency does not depend on the amplitude. Thank you.